Good morning, friends. Today I'd like to uh, do some problems for you. So first of all, I want to focus on infinite square well potential or particle in a box. Actually, in our notes, I gave you potential of this form. That is, V of x is equal to 0 for 0 less than x less than a and infinite when x greater than a and x less than 0. So, the potential look like this. So, we have a one dimensional infinite square well potential, or it's just like a box, one dimensional box. So, we are drawing it on the x axis. We have the side of the box as a, or the width of the well as a. So, 0 to a. So, between 0 and a we have potential V of x is equal to 0, and at the boundaries we have V of x is infinite, which is equivalent to a particle confined in a one dimensional box of side a. This can be written in a different way, that is, the width of the box here is a, that is a minus 0 a. If I design another well, infinite square well potential of width different from this, here I have a potential of width a minus a is equal to 2a. So, I have given a potential of width 2a here. So, based on the width, the energy Eigen values we evaluate from the Schrodinger equation will be slightly different in constants. Okay. So, in both the cases we have since potential is equal to 0 between the given limits, here it is 0 to a, here it is minus a to plus a, we can write Schrodinger equation, time independent Schrodinger equation in similar way for both the cases, because V is equal to 0. So, as usual, as you know, this can be given as k square, 2me by h cut square is a k square, and we write the Schrodinger equation in this form and we seek for possible solutions. Okay. So, in both the cases, if the potential is having a width a, width of the potential is a here and width is 2a here. So, in both the cases we have a same Schrodinger equation, and the possible solution is a sin kx plus b cos kx. Now, let us analyze what is the difference in energy Eigen values when we apply the boundary conditions, because the boundary conditions are different in both the cases. The only difference is with the width of the potential, but the boundary conditions are slightly different. So, let us apply the boundary conditions. This is the same case as we had in our notes. At boundaries, that is psi should be 0 at boundaries. Boundaries are x tends to 0 and x tends to a. So, for psi to be 0 at x equal to 0, we have the condition psi of 0 equal to 0 is equal to the first one, that is sin 0 will be 0 plus b cos 0 will be 1. So, that term will exist there. So, the only possibility for psi to be 0 is b to be 0, because cos 0 is 1. So, it will not tend to 0. So, we have to impose a condition that b is equal to 0. So, if we impose a condition, the solution, possible solution is put b is equal to 0 in the wave function. So, we will have the possible wave function having only the first term. So, we have psi of x is equal to a sin kx. Now, with the possible solution, let us apply next boundary condition, that is x is equal to a. So, for x equal to a, psi should be 0. So, a sin ka to be 0, what should be the value of ka? For a sine function to be 0, it should be multiples of pi. As you know, sin pi is 0. So, we impose a condition that ka, see this k is a small k. Okay. So, ka is equal to n pi. So, using that condition and applying the value of k square, we have the energy value, this one. This is what we have in our notes. Now, we are moving to the second case of width 2a, potential having width 2a. So, what will be the difference? Now, we apply the boundary conditions when psi of x tending to 0 at x equal to a and x equal to minus a. So, it is not simple like applying 0, x equal to 0. So, now we have two equations. So, when psi of a to be 0, we have a sin ka plus just apply x equal to a in the first equation. So, that is to be 0 according to the boundary conditions. So, a sin ka plus b cos ka is equal to 0. Also, when we apply minus a here, sin will be sin of minus theta will be minus sin theta. So, we will have a minus. So, a sin ka plus b cos ka. So, now we have two equations. So, a equal to b equal to 0 is not acceptable solution because we do not have any conditions from there and we cannot form the wave function accordingly. So, what we have to do is we have to consider two different conditions, either a equal to 0 or b not equal to 0, or a not equal to 0 and b equal to 0. So, apply these two conditions. So, first let us apply a equal to 0 and b not equal to 0. As you know, when a equal to 0 and b not equal to 0, when a equal to 0, this term will be 0, but when b not equal to 0, cos kx will not be 0. That means this to be imposed to 0. So, when we force cos kx to be 0, so for that value to be 0, we need ka to be n pi by 2 when n is equal to n varies like 1, 3, 5, that is odd numbers. Okay, when n is equal to odd, we have cos ka is equal to 0 when ka is equal to n pi by 2. So, only for odd values of n. So, from this condition we have energy which is slightly different from our previous value. Here we have 2 ma square, all the other values are the same, n square, pi square, h cut square by 2 ma square. Here we have 8 ma square. And apply the second condition. For the second condition, we have a not equal to 0 and b is equal to 0. When b is equal to 0, this second term is 0, but a is not equal to 0. So, we have to impose sin kx to be 0. So, sin ka to be 0 means ka to be n pi by 2 when n takes the values, that is even values. N takes even values like 2, 4, 8, etc. So, from this condition we have energy value n square, pi square, h cut square by 8 ma square. In these two cases we have the same energy Eigen value. Okay, but we have two different conditions for n equal to odd and n is equal to even. So, this is the difference between energy Eigen values in the case of the infinite square well with width a and width 2a. Now, let us find out the normalization. what is the difference between the normalization in both the cases. We have the first case, the limit from 0 to a, we have normalized as we have described in the notes. We have sin n pi x by a as a wave function, and we have integral limit is from 0 to a, psi n star psi n dx should be 1, and we have a star a is equal to mod a square divided by 2, that is when sine square, here we have psi n star psi n, so we have a star psi n pi x by a and a psi n pi x by a. So we have two sine functions, so we have sine square. So sine square x is written as 1 minus cos 2 x by 2. So we have this term 1 minus cos 2 n pi x by a, and this 2 is taken out of the integral. So we have integral a square by 2 into integral this one. So on integration we will have the second term getting 0 on applying the limits. So we have only the first term. Apply the limit, we have mod a square by 2 into a, only the upper limit exists. So we have a is equal to square root of 2a. But when we have width 2a, normalize it. This is the first case, that is for the odd values b cos n pi x by 2a. So if we normalize both the cases, odd or even value will have the same constant. So integral minus a to plus a psi n star psi n dx is equal to 1. So here we have the constant b. So in a similar way we have a cos square here, so we have 1 plus cos 2x. So mod b square, constant square divided by 2, this 2 is taken outside, this one, okay, 2 is taken outside, integral minus a to plus a 1 plus cos 2 n pi x by 2a dx. So like we have done here, we have here also the second term getting 0. So we have only the first term. So integral dx is x between limit minus a to plus a. So when we apply the limits, a minus a, the upper limit a minus lower limit minus a. So we have 2a here, and this 2 will be cancelled. So we have mod b square into a is equal to 1. That means the constant turns out to be 1 by square root of a. So that is the difference between the energy. So the wave function can be written as a square root of 2 by a, and here we have square root of 1 by a. So that is the difference in wave function and energy eigen values. If the limit is from 0 to a, that is the width is a, and here if the width is 2a, we have the eigen function and eigen value goes like this.